Okay, hopefully final day in lesson 2.7. I'm making it final day. I have no more days allotted for this. This was one too many days in my mind, but there has been a lot of information. So, and the physics component is a big piece of calculus. It is something we do see a lot. So, okay, so we're picking up on 19. And 19 is asking about the average speed over this 5-second interval. I'm trying to look here and process back. Because what did we do yesterday? Okay, so on 17 we did average velocity yesterday, didn't we? Okay, but when we talk average speed, well, think how is speed measured? Like when you're driving out on the road, speed is measured as miles per hour. So in other words, miles is a distance, hours is a time, right? So when we're talking about average speed, we're thinking in terms of distance divided by time. What is our distance here? Yeah, if you go back, that was question 15 that had total distance, yes? And then over this 5-second interval, so what is our time? And that's going to be 5. So we're looking here at 22.5 divided by 5, which is 4.5. And that was for average speed. Okay. What is the particle's acceleration over the first second, and what does your answer mean? So remember, first second is that horizontal piece of graph, yes? What is our acceleration over that first second? 0, because this is a velocity graph. Acceleration is the derivative. So acceleration is slope. And so we're going to, acceleration is 0. What does this mean? So I guess in relation to, if our acceleration is 0, what do we know about our velocity? It's constant, right? Okay. Over what time interval does the particle have positive acceleration? Oops, wrong way. Positive acceleration. Where do we have positive acceleration?
When slope is positive.
When slope is positive. So when is slope positive?
3 to 5.
3 to 5, yes? So we could also use the terminology positive acceleration. It is when velocity is increasing, right? Okay. So 3 to 5. And I am going to say when velocity increases. Or maybe I should say increasing. However you want to say it. Over what time intervals does it have negative acceleration? Yeah, 1 to 2 and 2 to 3, so 1 to 3. And that's, you're looking for your negative slope, and that's when your velocity is decreasing. Oops. So 1 less than t less than 3. And that is when velocity decreases. When is the acceleration undefined from 0 to 5? Okay, at t equals 3. Why t equals 3? Okay, that's a sharp point, sharp cusp, whatever vocabulary you want to use there. So t equals 3. Where else? Y1. Okay. It's a different type of sharp point, but it's not a curve. Okay, it's not a curve. Where else? 2. You're figuring out where I'm going with this, right? Okay, so we're going to talk about 1, 2, and 3 all being where acceleration is undefined, and that's because that's where the derivative does not exist, right? Acceleration is derivative of velocity. It does not exist. We're not talking about 0 and 5 because on the question it didn't include 0 and 5, right? So it's just from right above 0 to right under 5. So t equals 1, 2, and 3. And I'm going to say when derivative does not exist. So sharp points or cusp. Basically not your traditional curve and not just a solid line. Okay, 24. State an interval of time when the particle has positive acceleration but is slowing down. Positive acceleration but is slowing down. So 3 to 5, it's positive acceleration, right? Acceleration is increasing. But how do we know it's slowing down? Because even though acceleration is positive here, what do we know about velocity? It's negative. I had written that on this graph at one point, hadn't I? It's been a while. My graph's been erased, and I think I even erased it just to, give myself time. So 3 to 5, and that was when, how do I want to say this? They say, okay, we want our velocity to be negative, thus to have the opposite signs. For slowing down is opposite signs, so velocity has to be negative then. State an interval where the acceleration is negative, but the particle is speeding up. Wait. Acceleration is negative, but particle is speeding up. I disagree.
2 to 3.
2 to 3. Okay, so speeding up means we need what? Same signs, yes? So since speeding up, since acceleration is negative, right? Acceleration is negative, that means you need to know where A is negative and V is negative, yes? And so at that point, acceleration is negative from 1 to 2 and 2 to 3. But down here, so acceleration is negative on both of these, but velocity is negative down there, isn't it? Okay, so I didn't actually write my answer, did I? 2 to 3. What is the particle's acceleration over the interval from 3 to 4? Particle's acceleration, wrong way, 3 to 4. So here's my interval from 3 to 4. What do I need to find for acceleration? It's a velocity graph, so slope. What do we know about the slope here? We rise over run. We're going to rise how many? 5. We're going to run how many? 1. So 5 over 1 is going to be 5. And that's because we were doing particle's acceleration is the derivative of velocity, which is the slope of this graph. I guess I could have, I personally did rise over run. I want to say if I looked in the notes key, maybe they did a y minus y over x minus x. Okay, 27. What is the particle's average acceleration over the entire 5-second time interval? So when we did average velocity, it's up on 17. It's not on my screen, which is what I was just discovering. Notice we did the change in, distance over time. For average acceleration, we're going to want to do change in velocity over time. And so if I'm looking at change in velocity over time, my endpoints, so we're going to think v of 5 minus v of 0 over 5 minus 0. Okay. What is the velocity at 5? And what is the velocity at 0? 5. So we're going to say 0 minus 5 over 5 minus 0, which is going to be -1. Okay. And over what time interval is the particle's velocity decreasing at a rate of 5 feet per second every second? Where are we looking to find this? Velocity is decreasing at a rate of 5 feet per second every second.
Is it where the slope is?
Yep. We're looking for where the slope is -5 feet. And notice it says 5 feet per second every second. That's the same as saying 5 feet per second, which I don't know why. That's a typical thing, but I'd much rather say feet per second squared than I would per second. Okay, so velocity decreasing at a rate, then we're looking for acceleration, which is our slope. Where'd you find it at? I mean, it's either 1 to 2 or 2 to 3 because those are my negative slopes. Which one has the -5 slope? Yep, 1 to 2. Because you can go down 5, right 1. Okay. I was all looking at a velocity graph, right? Lots of questions, lots of connections. You guys didn't complain too much, so you must have followed for the most part, maybe. Maybe it's easier than I anticipate because, again, you're sitting in physics at the same time, so. Okay. Complete the table below to find all the possibilities for an object's motion. So we're talking about the speeding up, slowing down type business. Remember that an object's velocity is either positive, moving right or up, negative, moving left or down, or 0, as in stopped. Also, that an object's acceleration is either positive, negative, or 0, as in constant. So, some of this we definitely should know by now, so we may have to discuss a little bit. So, first box. When the velocity is greater than 0 and acceleration is greater than 0. What are we doing? Okay. Increasing is in speeding up. And we're speeding up because they are both positives, right? Same sign says we're going to be speeding up. Okay. Let's just go across to the... You want to go across or down? I'll go across. What about when my velocity is greater than 0, but acceleration is less than 0? Opposite signs. So we are what? Slowing down. What about when our velocity is positive, but acceleration is 0? Okay, so it's constant, right? That acceleration of 0 means we're constant, and because the velocity is positive, it means we're going to the right. So constant. I'm going to say velocity to the right. Okay. Next row. What about if my velocity is less than 0 and my acceleration is greater than 0? We are slowing down because there's opposite signs. Sorry, I didn't wait for you. What about if velocity is less than 0 and acceleration is less than 0? Speeding up because they are both negatives, same signs. What about when the acceleration is positive but velocity is negative? Or excuse me, acceleration is 0. Okay, again, it's constant. When that acceleration is constant, or acceleration is 0, that means we're going constant. Because it's negative, it's going to go left. Okay. Now, what about when the velocity is 0, but the acceleration is greater than 0? Okay. So officially, because the velocity is 0, it's technically a brief stop, right? I mean, officially we say stopped, but okay, we can talk changing direction. What is that positive acceleration going to do? That's because it's positive, we're going to say right or up. Okay, so yeah, so the object is stopped. The acceleration is going to cause up or right. So if velocity is 0, but acceleration is negative, again, the particle or object is stopped this time. Acceleration down or left. And what if the velocity is 0 and acceleration is 0? You just stopped. There's no acceleration there. So I'm going to say stopped, and since I've been commenting on acceleration, no acceleration. Okay. No acceleration in this one, whereas the others we are accelerating up or to the right, accelerating down or to the left. Okay. Some of these charts are going to be helpful as references, yes? The top of the next page is another chart. We're full of charts here. And it definitely has some good definitions in it, some helpful information. I'm sure you can always make some notes and add more if you need to. Displacement over an interval. Remember, displacement is not total distance, but total change in position. So with displacement, you're not looking at, oh, we traveled 5 units forward, then 2 units back, plus 6 units forward. You know, you're not adding all those up. Total displacement is, I started here, I did a bunch of stuff, I ended here. What's the difference between my beginning and end? Average velocity, displacement over elapsed time. So difference from beginning to end over time. Also, you'll notice it's listed as slope of the secant line. Velocity at time t, you already know, velocity is derivative of the position function. It's also the slope of the tangent line. Speed, absolute value of velocity, so absolute value of the derivative of the position. Distance traveled, the sum of the absolute values of the distances between turning points. So that's taking all your distances and adding them up. And direction changes. When velocity changes from either positive to negative or negative to positive at a point, velocity does not need to pass through zero or even be defined at a point where its sign changes in order for direction to change. Okay, so when we're changing from either positive to negative or negative to positive, does not even need to pass through zero or be defined. It's the sign changes that cause the direction change there is what that's saying. Okay. Ready to launch a rocket? Let's go launch a rocket. A model rocket is launched vertically upward from ground level with an initial velocity of 114 feet per second. The position of the rocket can be modeled by the given function s of t. Have you guys noticed the little calculator emblems at times? Okay, that is the author's way of saying this is a calculator active problem, like you would be expected to use a calculator. Okay, a lot of what we have done in here, we haven't really been using calculators a ton necessarily. I mean, there are times we pull them out for this or that. We haven't used them a ton, but there are things that, you know, this is definitely a calculator active problem. If nothing else, just because of the math we have to do here. Okay, A, find the velocity and speed of the rocket at t equals 5 seconds. Okay, what am I doing? Finding the what? Derivative. So in order to find velocity at 5 seconds, we first have to find a velocity function, which is derivative of the position function. What is that derivative? Agreed? Negative 32t plus 114. Okay. So if they want the velocity at 5, so we're plugging in 5, right? Negative 32 times 5 plus 114. That's where the calculator comes into play. I don't know what that answer is. If you try it, should be getting negative 46, I believe. That's negative 46. If you look back at the units of the problem, feet per second. It asked us for velocity. It also asked us for speed. What is the speed? What's the speed if velocity is negative 46?
Value of negative 46.
Right, absolute value. It's going to be the absolute value of velocity at 5, which is going to make it positive 46 feet per second. Is that better today?
Yeah.
Okay. B. Is the rocket speeding up or slowing down at t equal 5? Explain how you know. Well, what do we have to know to answer this before we can even talk about speeding up or slowing down? We have to know acceleration, don't we? We have already talked about velocity, but we have to know acceleration. So acceleration is the derivative of velocity or the second derivative of position, yes? And let's see. First derivative was negative 32t plus 114. What's second derivative? Negative 32. So what does that make the acceleration at 5? Negative 32. There's no place to plug t in, so your acceleration is just negative 32 everywhere. So, speeding up or slowing down? Speeding up because the signs are the same. So, whoops. Rocket is speeding up, and I'm going to say because the velocity at 5 is less than 0, and the acceleration at 5 is less than 0. In non-mathematical words, I just said they have the same sign, yes? But mathematical justification, a way to say they have the same signs is that pointing out that the velocity is less than 0 at that point and the acceleration is less than 0 at that point. Okay? What is the maximum height the rocket will rise? Where are we going to find the maximum height? Yep. We are looking for when velocity equals 0. My velocity equation was negative 32t plus 114 equals 0. If you either subtract 114 over or add 32t over, you have 32t equals 114 or negative 32t equals negative 114. And I don't know, what's 114 divided by 32? Go ahead.
3.56.
Okay. 3.5625. Now, what is that 3.5625? That's t. That's time. That's seconds. What was the question? Maximum height. So if I answered the question, I've answered when does the maximum height occur. This question is asking what is the maximum height. So now what do? Plug it in where? The position function, right? Because your position function, when you plug that time in, is going to give you the position at that time. If we plug back into velocity, we're just going to get 0. Okay, so we're plugging into the position function. So I'm going to say S of 3.5625. And then in all honesty, if you're on a calculator active portion, you can write that and then just write your answer. Because that is stating that you're plugging in the 3.5625 into the calculator, into S. Okay? You got a number in the 200s? .0625, and that would be feet. Okay. Okay. And lastly, what is the speed of the rocket when it hits the ground? What do we need to do here? When does the rocket hit the ground? What is 0? Position. You're looking for when is the position 0. Okay? And then going from there. So position formula was negative 16t squared plus 114t equals 0. I can factor out a GCF there because it's a t squared and a t term, right? So I don't want to try and move anything over. I want to keep it equal to 0. I can factor out t. 114 doesn't divide by 16, does it? I don't think it does. No. But 16 and 114 are both even. So I can divide them by 2. I'm going to factor out a negative 2t, just because I like to have my first term positive also. So if I factor out negative 2t, that's going to leave me with 8t minus something. 57. I have two factors multiplying to equal 0. So set each part equal to 0. Negative 2t equals 0. Or 8t minus 57 equals 0. So we get values there of 0 and whatever 57/8 is. I think honestly I just left it as 57/8 because it was just easier that way. Okay. Have I answered the question yet? No. This answers when does the rocket hit the ground. So when does the rocket hit the ground? At 0. And what's that 0 indicate? That it starts on the ground. And then it hits the ground also at 57/8. How are we going to find the speed when it hits the ground? Velocity, right? Speed is absolute value of velocity. So we're going to do the absolute value of the velocity at 57/8. Am I making sense there? So I'm going to plug 57/8 into, somewhere here I have a velocity equation. Negative 32 times 57/8 plus 114. Negative 32 times 57/8 plus 114. Realize, don't take the absolute value to get to the very end, yes? Absolute value does not make anything positive other than the final answer. Okay. What are you getting? I say officially it's the absolute value of negative 114, isn't it? Which makes it 114. Speed is going to have the same label as velocity, so feet per second. Okay. Last page, right? Okay. We know that for very small values of h, the approximation of the derivative can be found by the difference quotient. So that's what we use for definition of derivative. It can be shown that the approximation can be found when h equals 1. Now that is the derivative of x naught is approximately f of x of 0 plus 1 minus f of x naught. So basically saying there that in order to find the derivative at a point, you can do the difference quotient between that value and a value very close, like the next value up, so to speak. So to clarify, the derivative is approximately equal to the change in f caused by a 1 unit change in x when x equals x naught. And if I recall, we use that here. I'm assuming that's why we're talking about it. Yeah. So for speeds between 30 and 75 miles per hour, the stopping distance after the brakes are applied for a vehicle can be modeled by this formula. For a vehicle traveling For a vehicle traveling at 65 miles per hour, we're going to do the following stuff. Okay, find the actual stopping distance at 65 and 66 miles per hour. And then what's the stopping distance needed for an increase in speed by 1 mile per hour? So, actual stopping distance for 65 and 66 miles per hour, we need to find f of 65, right? Which, I don't know, I can write out 1.1 times 65 plus 0.05 times 65 squared. I don't know if I really need to write that, out, because if I say f of 65, you guys understand that that's plugging 65 in, yes? And we plug it in, we get did you get it? We have 282.75. And this is a stopping distance, so this is going to be feet. We're also asked to find f of 66. So 1.1 times 66 plus 0.5 times 66 squared is some number. And this is where if I'm using my calculator, I've already typed it in once, I'd go up and copy that down in my calculator and then just change those values. What do we have? I have 290.4 written in my notes. Okay. So when we're at 65 miles an hour there, 66 miles an hour, what is the stopping distance needed for an increase in speed by 1 mile per hour? So what am I going to do to find that stopping distance needed for the increase in speed by 1 mile per hour? Basically, what's the difference between these two values, right? So I'm going to write it as f of 66 minus f of 65. Subtract those two values. And I have 7 and 6,500 feet. B when you're ready. Estimate the change in stopping distance if the speed is increased by 1 mile per hour by using the instantaneous rate of change at s equals 65. Okay, so we just used the formula. Found f of 65, f of 66, subtracted those to find the stopping distance between the two. Now, instead, they're asking us to do instantaneous rate of change. What are they saying there? How do they want us to do this? Instantaneous rate of change is represented by which is the derivative. Yep. So let's find f prime of s. I hate using s's. My s's and 5s are so hard to keep apart. So the derivative of the function is 1.1 plus 0.1s. Is that right? So if we're asked to estimate that change in stopping distance at s equals 65, so now we're going to find f prime of 65. So whatever 1/10 times 65 is going to be 6.5, plus 1.1 is going to be 7.6. This is stopping distance again, so this time we're going to say feet. Okay. And then C basically says, oh. Okay, I just looked at my label. officially on this one, and I guess for all of them we could say this, but my label is a little bit more than just feet. Because if you think about it, a derivative is a rate of change, yes? I keep saying that. Derivative is a rate of change. So it's not going to be feet, it's going to be feet per, what is that? That is 7.6 feet per mile per hour. So, okay, when we compare these, okay, wait a minute, I'm confusing myself. Compare this estimate with the actual increase in stopping distance. I'm not doing what I thought I'm doing.
Because isn't the actual stopping distance an over? Wait, no. The estimate is an underestimate when compared to the actual.
Yeah, what I wrote down in my answers does not make sense here, though. Okay. I mean, my notation here that I wrote is not making sense. I'm not sure what I was meaning to myself, or if I got distracted and didn't finish writing. I don't know. It's not making sense what I wrote here. So, but yes, they're very close, aren't they? And that's what, that we have to notice that they're very close. The actual stopping distance is technically a teeny bit longer, isn't it? But other than that, they are very close. But in general, for an increased speed of 1 mile per hour, there you have to allow 7.5, almost 8 more feet to stop. Okay. Yeah. Okay. So I'm going to say actual stopping distance I'm just going to say is very close, because it is very, 500ths, that's not much in terms of, looking at distance. So actual stopping distance is very close to estimate. And I'm also going to say at 66 miles per hour, stopping distance increases by about 8 feet. Okay. Yeah, go back and look and see what I really meant to have written there, because what I have written does not make sense. Okay, guys, you have a few minutes. You can work a little bit on homework, can't you? So, homework takes you through several different situations and a lot of the different vocabulary. So, have homework done for tomorrow, please.